One of the variations that we might see on the disk method is called the washer method. And it's named the washer method because if you look at the slices that we were talking about earlier, and you pull those slices out, they're not completely solid. They have a hole in the middle, kind of like a washer. So before we actually get into formulas and examples, I again want to show you a picture of what this is going to look like and give an explanation of exactly how we're going to approach this. We still are going to use the basic disk method formula. We just have to make a couple of little adjustments. So the washer method is for when the volume is not completely solid, when we see that there's some hollowness inside of it. And this occurs specifically when we're not using our axis of revolution as our bottom boundary. We have some other function that we're given as our bottom boundary. So let's take, for example, the region that gets enclosed by f of x equals x squared. And then f of x equals 1/2 x squared, which is a little bit wider. This one's going to be g of x. So at x equals 1, our f graph is up at 1, but our g graph is at 1/2. And then at 2, the f graph is up at 4, but 2 squared is 4 and half of that is 2, so the g graph is at 2. And then we're going to go ahead and just cut this off at 2, so I'm going to say from 0 to 2. So if you look at the region that's enclosed between f of x equals x squared and g of x equals 1/2 x squared on 0 to 2, we're going to revolve this about the x-axis. So just like the basic problems we saw in part 1, we still are going to have a two-dimensional region to start with, and we still want to revolve that around the axis of revolution that we're given. When we get to 180 degrees, we are going to have an exact replica of it. It's going to be the, let's see here. Let's say that's my little one. That's my big one. It's not perfect, but we're going to have the reflection of it over our axis of revolution. And we're going to have these circular paths just to follow the edge to see what happens. So not only the outer edge gets spun, but that inner edge is getting spun as well. And then we've got all these arcs, because it's happening at every point along the graph. So because we have an outer function and an inner function, this is not completely solid. That bottom function, g of x equals 1/2 x squared, is stopping the volume from going all the way through the center and connecting to the other side. There's actually hollowness inside of here. We could stick our finger in there, and there's air space in here. So if you were to take a slice of this and pull it off to the side, it would actually look more like a washer. And obviously you cannot see the three-dimensional aspect of it. That's a little bit harder to draw. There we go. It's kind of. There we go. That's my best. But because there's an outer and inner boundary, we've got some hollowness in the middle of our discs. So they're actually called washers. They look like the washers we use in mechanics. So the volume here, we have to include both of those functions. And technically, both of those functions can create a volume. The f of x equals x squared creates a volume. It creates the big outer volume. But we don't want all of the big outer volume. We want to scoop out, for lack of a more technical term, we want to scoop out everything that's inside the g of x equals 1/2 x squared function. And when it gets revolved, that also is going to be a volume inside. So we're not just going to do top function minus bottom function. It's technically outer volume minus inner volume. And it will account for that hollowness. Another example that doesn't really use graphs and calculus yet is if you had like a a shell. And I guess we could apply this and just talk about area for now. If I wanted to know the area for just the shaded region, and I know that the radius out to the big circle is 5, and the radius out to the little circle is 2. Think about how exactly you would find the area for that shaded region. Just like we said right above it, we would do the outer area minus the inner area. Everything that we need is inside of that circle of radius 5, but I want to exclude anything that's inside the circle of radius 2. So we would do outer, but we would do our calculation that we need, and then we would do inner of the calculation that we need. Don't just subtract and say, well, 5 minus 2 is 3, so I can just do the area calculation with 3. That is not going to give you the same answer. We need to know the area of a circle of radius 5, so we're going to do the area of the large circle minus the area of the small circle. And that will give us the area of the shaded region. And we're going to use this exact same approach with these volumes of revolution that have hollowness. So the area for a circle is pi r squared. So if we do this off to the side here, the outer radius is 5, so we would do pi times 5 squared. And then our inner circle has a radius of 2, so pi times 2 squared. And we would want to know what those are individually first. So I've got 25 pi minus 4 pi. So all of the area is enclosed inside the circle of radius 5, which has an area of 25 pi. But I want to take out the area that's inside the circle of radius 2, and that has an area of 4 pi. So if I take out the 4 pi area, I'll be left with just the area of the shaded part, which is 21 pi. And we're going to do the exact same thing with ours. The idea here is that these two get squared separately. We don't subtract first and then square. we square first and then subtract. So to deal with washers, we want to do our outside function and figure out the volume that it gives us. But then we want to kind of scoop out and subtract the volume from the inside function, because anything from that inner function is where our hollowness is, and that's not going to be included in our volume if it's hollow. But because these two integrals have the exact same boundaries from a to b, we can really just include them in one integration. We can say this is the integral from a to b of pi times f of x squared minus g of x squared. The most important thing is that you recognize when you're dealing with a solid of revolution that has hollowness, you have to square these separately. Think of it as an outer volume minus an inner volume. And that's why we're squaring separately, because we're technically calculating their volumes individually and then subtracting. But we don't actually have to work out two separate integrals, because there's so much in those integrals that they have in common. We could really just do it all inside of one integral, as long as we remember to square them separately. So let's go ahead and try to work out this problem we have written here. If you draw your slice, and I'm going to redraw this because it's already kind of busy right now. We've got the x squared, and then we've got a half x squared, and we're cutting it off at 2. So there's our region. There's our two-dimensional region. Oops, sorry. That's 2, and they connect over here at 0. If you take a slice, and the slices maybe didn't seem so important in part 1, but they're a little bit more important here. So now if you take a slice inside of this region, we're trying to stay inside the region, you can see that the outer boundary is the x squared, and the inner boundary is the 1/2 x squared. Outer or top boundary is our f of x equals x squared. And then our inner or bottom boundary is the g of x equals 1/2 x squared. And both of these functions on their own are capable of creating a volume. And we want to do the outer volume minus the inner volume. So when we set this up, since we're going around the x-axis, everything's going to be in terms of x. We want our functions in terms of x. We're going to integrate with respect to x. And then we also want our limits of integration to be x values. So for our volume, we can see on the x-axis that that original region that we drew extends from 0 out to 2. So we're going to be integrating from 0 to 2. Our top or outer boundary, that's the one that's going to create a larger volume. If we just were to look at that one, the volume would come out bigger. And I know to use that one for the outer or the top because it has larger y values. If it has larger y values, then it's farther from our axis of revolution, and it's going to create a larger volume. This is going to be a subtraction problem in here, and volume should always come out positive. So you should always have the larger one first and the smaller one second. So the outer one there, or the top one, is the x squared graph. And remember, With these, we're squaring them because it's based on the area of a circle or the volume of a disk, which is pi r squared. But then we want to subtract the inside, which is bounded by the g of x equals 1/2 x squared. And we're doing volume, so we square it. So we've got an outer boundary squared minus an inner boundary squared. And again, the most important thing when we're doing washers is that we realize they get squared separately. So we're going to clean this up a little bit and then we'll be ready to integrate. So just ignore the pi for now because we're going to get an exact answer. So x squared squared is x to the 4th. And then be careful with your squared here because we've got to square the coefficient and the variable. So this is going to end up being minus 1/4 of x to the 4th. And since those are like terms, we could really clean it up even more. This is 3/4 of x to the 4th. And now we're ready to integrate and get our volume. So the antiderivative for 3/4 x to the 4th, we're going to increase our exponent by 1. So it's going to go up to x to the 5th. And then we divide by that new exponent. So if we include that with the 3/4 that we already have, it's going to turn into 3/20. We need to evaluate from 0 to 2. You always plug in your larger number first, your top number. So 2 to the 5th is 32. 32 times 3 is 96. And if we plug in 0, we're going to get 0. And 96 over 20 can be simplified a little bit. They both have a factor of 4. If we pull out a factor of 4 in our 96, I believe we're going to get 24 over 5 pi. So we've got this outer boundary and the inner boundary. And we're not using the axis of revolution as our inner boundary or our bottom boundary. We've got a different graph doing that for us. And whenever that happens, it creates a hollowness. So we've got to think of it as an outer volume minus an inner volume. And we square separately. So let's look at one more real quick. We're going to find the volume of the solid of revolution. Formed when the region bounded by y equals x squared and y equals 2x on 0 to 2 is revolved about the y-axis. This is still technically the disk method, so everything we talked about earlier with the disk method still applies. Since we're going around the y-axis, we are eventually going to have to get everything in terms of y. But don't worry about that yet. Only worry about that when you're ready to set up your integral. For right now, let's draw our graph. Let's see what this region looks like. Y equals x squared is a parabola. We're only interested in the piece that goes from 0 to 2. So y equals x squared goes through 0, 0, 1, 1, and 2, 4. And then we've got another boundary, y equals 2x. Y equals 2x goes through the point 0, 0, 1, 2, and 2, 4. And it's a straight line. So we've got our parabola that's curved, and we have our line that is straight. And we're just worried about the 0 to 2 boundaries. So we've got our region here. that gets enclosed. And we want to revolve this around the y-axis. Now that's something that's different on this one. Go around the y-axis. This is supposed to be an arrow. I know it's not very clear. Now when we start to revolve this around the y-axis, when we get to 180 degrees, we will have the reflection of it. So we will have a straight line that goes from 0, 0 to 2, 4, and then we'll have our parabola. And then it's going to have circular cross sections. So this one again is like a bowl, but this time we do have some hollowness inside because we're not going from x squared all the way to the y-axis. This y equals 2x line is stopping us from filling this in all the way to the y-axis and making us solid. It's stopping us at that slanted line and making all of this space in here be hollow. So to help decide which function to write first and which function to write second, you need to draw your slice. And remember, the slice is always perpendicular to the axis of revolution. So here's your slice. You can draw it all the way to the axis if you want, especially because this one's kind of small. There's my slice. You need to see which graph it crosses first, which one is farther away from your axis of revolution. Here's our axis of revolution. The one that's farther is the one we want first in our integral. That's the one that creates the larger volume. And then the one that's closer is the one that we're going to write second in the subtraction problem. That's where the hollowness starts. And that one is creating a smaller volume. And we need to make sure that subtraction problem always comes out positive. So we always want to do larger minus smaller. But since we're going around the y-axis, everything in that integral has to be in terms of y. So y equals x squared, we have to rewrite as x equals square root y. We also had the line y equals 2x, which we'll have to write as x equals 1/2 y. So I'm just using algebra to isolate the x. And then it rewrites it as a function of y. So it's the parabola that is farther away. That's going to be our outside function. And it's the line that's closer. We're not comparing this to the x-axis. It would be a whole different story if we were comparing it to the x-axis. They told us to revolve it around the y-axis, so we have to compare their distances to the y-axis. The parabola is farther, the line is closer. So the parabola is the outside, and the line is the inside. Our limits of integration also have to be y values. So we want to see on the y-axis how low it goes, which is 0, and then how high it goes, which we found to be 4. So for our volume, we're going to be integrating from 0 to 4, and we always have a pi. And remember, those boundaries get squared separately because both of them creates a volume. We want all of the volume inside of the square root y function, but then we want to scoop out the volume and create the hollowness inside of the 1/2 y function. And then we'll just clean it up a little bit so we can integrate. I'm going to pull my pi out and just wait till the end for it. I'm going to square a square root here, so that just ends up y. And then be careful because you're squaring the coefficient and the variable. That's 1/4 y squared. And we can't combine these. They are not like terms because they have different powers. So we've got two terms to integrate here. The antiderivative for y is 1/2 y squared. The antiderivative for y squared, we're going to increase that power, and then we're going to divide by the new power. We already have a quarter out front, so if I now also include a 1/3 out front, it's going to multiply and turn into a 12th. We need to evaluate this from 0 to 4. When I plug in 4 4 squared is 16, half of that is 8. 4 cubed is 64. For right now, I'm just going to write 64 twelfths. So this is what we get when we plug in 4. And then when I plug in 0, I just get 0 minus 0, which is 0. So we just have to figure out what 8 minus 64 twelfths is. 8 is going to be 96 twelfths. So 96 minus 64 is 32 twelfths, which is still not simplified. They both have a 4 in common. So let's see if we could pull out a 4. That's going to be 8 pi over 3. You could certainly do this in your calculator. If you asked your calculator what 8 minus 64 twelfths is, it's going to give you a fraction, or excuse me, it's going to give you a decimal. And we don't want a decimal. We want an exact fraction. So if you type in your calculator 8 minus 64 twelfths, it says 2.666666, and then the very last number it gives you is a 7 because it can't write any more numbers, so it just rounds the last number. You want to change this to a fraction, and the way that you do that is you do math option 1, which has a triangle, which on our calculator represents change to a fraction, and hit enter twice. So with this 2.6666 number on my screen, I just hit math option 1, enter, and it changes it to 8/3. So you don't have to be real quick with all of these calculations and all of these fractions and being able to do all this stuff by hand. Certainly you're allowed to use your calculator on all of this as well. But don't forget about your pi. We don't ever include the pi while we're doing the integration. We just always throw it onto our answer at the end, and that will keep our answer exact. Okay, so this works whether we're going around the x-axis or the y-axis, and all of the rules that we learned in the last part are still true, where if you're going around the y-axis, you have to be in terms of y. If you're going around the x-axis, you have to be in terms of x. When you draw your slices, you always are going to draw them perpendicular to your axis of revolution. That helps you decide your radius function. It's even more important here with the washer method because it's going to help us decide who's farther away and who's closer. So with the slice we drew here, it's easier to see with that slice that the curved graph is farther and the line is closer when we compare it to the y-axis here. We always want the one that's farther away to be written first because that one creates the larger volume, and we want the one that's closer to be written second in the subtraction because it creates a smaller volume, and that way our subtraction always comes out to be a positive number. So the last thing I'm going to show you real quick to finish up this section is what to do if we were asked to revolve around something other than the x-axis or the y-axis. And I'm only going to show you this for horizontal lines. If we were asked to do some horizontal line other than the x-axis. In section 4, we're going to actually learn a much easier way to revolve around different vertical lines other than the y-axis. So this last little subsection here of section 3 is other horizontal axes of revolution. And this is the last little variation that we'll see on our disk method, or our volumes by slicing. So these other horizontal axes of revolution will be given to you as y equals some number. They'll say revolve it around the line y equals 2 or y equals -5. And we want to know what exactly that's going to do. How is that going to affect what this looks like, and how is it going to affect the setup of our volume calculation? And it's really not that difficult. It really just goes back to a concept that we learn in algebra. So we're going to start with just a really simple example. So if we were asked to find the volume and I'm going to say we're going to do, let's just do a straight line for now. We're going to revolve y equals x plus 3. 1, 2, 3. That has a slope of 1 and an intercept of 3, and it's just a straight line. So we've got this straight line here. We also have y equals 3, which is a horizontal line. That's also a boundary. And we have x equals 2. So those are the boundaries for our region. And if you draw all of those, you will see that they do enclose this little triangle. And we're not going to revolve this around the x-axis or the y-axis. We're going to revolve it around something different. We're going to revolve this around y equals 1. Now, drawing this solid can sometimes be kind of tricky. I like to mark where my axis of revolution is with a dotted line. That's going to be helpful. We never did this before because it was always the x-axis or the y-axis, and we already have those drawn. But I need to revolve my little yellow triangle here around that line. And when you revolve, your reflection is always going to be an equal distance below and above. So right now, excuse me, if we compare that triangle to our axis of revolution, which is y equals 1, the base of that triangle is exactly 2 units above. So when I draw the reflection, it needs to be exactly 2 units below. So 2 units below 1 is -1. So I don't go all the way down to -3. That would not be revolving around the line y equals 1. That would be revolving around the x-axis. That's not what we want. And then we have this slanted line, and we can finish out our triangle. And as it spins, it's going to create our circular cross sections. So we see there is hollowness in this one. So we're really going to be using the washer method. But we also have to account for the fact that we're not going around the x-axis. We're revolving around y equals 1. And this is actually pretty simple to fix. And like I said earlier, it's just an algebra concept. What we're going to do is shift everything down 1. We want to make it so that axis of revolution that they gave us lines up with the x-axis. And it will if I shift it down 1. And I'm allowed to do that as long as I do it to everything in the problem. Shift everything down 1. And back in algebra, the way that we shift things up and down is we just add or subtract from the functions. Add will shift it up, subtract will shift it down. So technically, my y equals x plus 3, if I shift that down 1, I shift it down 1 by subtracting 1 from it. And really, it's going to turn into y equals x plus 2. And then my y equals 3 graph, if I want to shift that down 1, I have to subtract 1 from it, and it turns into y equals 2. If we look at the solid that these two new graphs make, it's going to end up being the exact same solid we just had, but shifted down 1 unit. And that's going to make our axis of revolution, which we technically also should subtract 1 from. If we do that, we get y equals 0, which is the x-axis. So it's just going to make it so that we have the exact same volume, except now it's revolved around the x-axis. So y equals x plus 2 has a y-intercept of 2, and it's got a slope of 1. So right 1, up 1, right 1, up 1. And then the line y equals 2 is a horizontal line at y equals 2. And we were given a specific interval. Nope, we were given x equals 2. We don't need to subtract from the x because we're trying to shift up and down. Shifting up and down happens along the y-axis. So we only add or subtract from the y equations or from the y values. So that triangle looks identical to the triangle we just had. It's just shifted down 1 unit now. And now we can think of it as a revolve around the x-axis problem. So now, when we look at the reflection, this triangle went up 2. So for the reflection, it's going to go down 2. And then we've got our slanted line. And then we have our x equals 2 line. And we're going to have our circular cross sections. It is the exact same solid. It's just shifted down so that our axis of revolution matches up with the x-axis. Now we can draw our slice. And we always compare this to our axis of revolution, which is horizontal here. It's now the x-axis. So our slice is vertical. And we want to start with the one that's farther away because that's going to create more volume. So the one that's farther away is our slanted line, y equals x plus 2. And then our hollowness starts at y equals 2. That's the closer one to the x-axis. So our volume is the integral from 0 to 2 pi times the outer boundary squared minus the inner boundary squared. And those aren't the same two functions they gave us. We had to shift everything in this problem down 1 unit, and it was based on the axis of revolution they gave us. Now, if they gave us y equals -3, in order to get that to line up with the x-axis, we'd have to shift everything up 3. So we would add 3 to all of the y's in the problem. So you could shift up or down. Do whatever you have to do in terms of shifting up or down on all of your y equations. A shifting is called a rigid transformation. It doesn't change the size or the shape of the graph. It just changes its location. And as long as we do it to everything, it won't change the solid that we're creating either. So it's still the exact same solid. It's going to have the exact same volume, but now we can easily put it into our washer method formula since it's a revolution around the x-axis. Sometimes the setup is the hardest part. Now we just need to clean it up a little bit. This, be very careful, this has to be FOILed because it's got 2 terms in it. It's a binomial. So that's x squared plus 4x plus 4. And then 2 squared is 4, so we're subtracting 4. And I'm just going to clean it up a little bit more. I'm going to pull the pi out. We'll just worry about that one at the end. And that plus 4 minus 4 ends up canceling. So it's just x squared plus 4x that we're going to integrate with respect to x. So our antiderivative is 1/3 x cubed plus 2x squared. That will evaluate at 2 and at 0 and then subtract. If we plug 2 in, 2 cubed is 8. Divide by 3, we're just going to say 8/3. And then 2 squared is 4 times 2 more is 8, so plus 8. If we plug 0 in, we're just going to get 0. So I've got 8/3 plus 8, which is 32/3. So I've got 32 pi over 3. So to deal with these different horizontal axes of revolution, other horizontal axes of revolution, all we're going to do is shift. It's the algebra shifting that we learn back in pre-calculus algebra. We're just going to shift everything either up or down. Up is plus, down is subtraction. And that's so that the given axis of revolution lines up with the x-axis. And we do that before we do anything else. So I did that before I set up my integral. I like to do that first. So I shifted my x plus 3 down, that got me x plus 2. I shifted my y equals 3 down, that got me y equals 2. Now I've got the two functions that I can use and set up in my Washer method formula and square and subtract. And we get 32 pi over 3. Now for different vertical axes of revolution, we're actually going to learn a completely different method that's going to be much easier. So for right now, just worry about different horizontal axes of revolution. And in 6.4, we're going to learn something called the shell method. In our textbook, it's actually called volume by shells.